Hi, everybody. Thank you for the reminder. I am recording right now. So, yesterday we looked at the base 60 system for Babylonian math, and today we're not going to be utilizing uh, base 60 because what base you're in doesn't matter as far as like algorithms go. There are sometimes some algorithms throughout history that would have been different if the culture had a different number system or it's like unique to their number system. But for today, we're looking at quadratic equations in Babylonian times. And it's all going to be done in base 10, although there's going to be like a little project where we look at a source material, and that source material is going to be in base 60. But for today, it's almost all base 10 now. We looked at the base 60, and just to give you an opportunity to just see how they were very clever with what they had, and the choice of 60 and how that allowed them to represent things like 1/3 and 1/6 and 1/9 with terminating decimals was really good. Now, why they use 60 and not 30, I wasn't sure, but still things to think about. Now, there were a bunch of tablets found in what's now Iraq, and it indicated that the Babylonians had a process for solving quadratic equations. And they essentially could solve, any quadratic equation, although they would only make up ones that had rational solutions. But essentially, they could do just like now we do quadratic equations. They did them, and this was notable because quadratic equations are not like especially practical in the real world. Like this question that's on the screen now, x squared minus 8x equals 33. Why, for practical purposes, would anyone want to know that? Now, they would write this question sometimes in as a word problem. They might say something like this: the area minus the area of a square minus 8 times the square side is 33. And that is, so the area, if the square is x by x, then the area would be x squared. The square side would be x, so minus 8 times. But that's still not a practical question. Math was originally invented as a way to do practical things with money and counting your livestock and how much land you have and money. So it's interesting to me that in 1600 BC, they were sophisticated enough to be making up math problems that really don't have any practical purpose. Why would I want to know what the length of a side of a square is if the area minus 8 times the square side is 33? Someone asked about yesterday. No, I hadn't posted. It's a sort of process where when I do a recording, it doesn't end up on my computer. It ends up on this like Zoom server that I have to go and type in a thing, and it takes a while to process. Although it has processed, I'll put that up today. And there won't be a live lesson the rest of this week, so it will all be the videos. Yes, and I see comments about quadratics do have practical purpose in the real world now. There's plenty of opportunities now, but I guess what I mean is back in 1600 BC, they weren't, these were like questions they were answering basically for the sake of answering questions and not because the questions that they solved were practical. But yes, now there's plenty of good applications of quadratic equations. Now, what are the three main ways to solve this equation, x squared minus 8x equals 33? You could type them into the chat. What are the ways that, if you had to solve this question, what three ways could you use? So I see factoring and quadratic formula. There's a third way that hasn't been mentioned yet. The factoring the quadratic formula would require you subtract the 33 from both sides. What is another way of doing this that's in some ways more fundamental than the quadratic formula? I guess I could ask, like, where does the quadratic formula even come from? How do you derive the quadratic formula? Okay, I'll refresh your memory. What do the words completing the square mean to you? Or if I said, I want you to do this x squared minus 8x equals 33 using completing the square, how would that look? That's not factoring or the quadratic formula, but it is a fine way to solve this. What does that mean, completing the square? Or how do you complete the square? That's right, you add 16 to both sides. You complete the square by, when you complete the square, it's good to have the constant on the right-hand side. So you take half the b term and square it, negative 8 over 2 squared equals 16. And you add that to both sides of the equation. (33 plus 16 is 49. By adding the 16 here, this thing on the left becomes x minus 4 squared. And then you can take the square root of both sides. X minus 4 equals plus or minus 7. And then finally, you can add 4 to both sides. So x equals 4 plus or minus 7, which is 11 and negative 3. So there are 2 inches. So that's the completing the square process. Just want to kind of remind you of that because we're going to revisit that a little later. One way that nobody would consider doing would be to factor the x out. We're going to see today the Babylonians did do it that way as their first step, and we're going to see how that works. But before we get to that, let's look at how their quadratic equations work. I've already mentioned that you could create a contrived situation like the area minus 8 times the side, the square side is equal to 33. But a very popular question that actually reappears throughout history is find two numbers so that the sum is, you're given the sum and the product. This particular system of equations, where you're given the sum of two unknown numbers and the product, that appears throughout history. And what's the answer? Just through guess and check. It is 7 and 3. Now, the Babylonians, so nowadays, the official way of solving this question would be to replace y with 10 minus x, and then use substitution. X times 10 minus x equals 21. 10x minus x squared equals 21. X squared minus 10x plus 21 equals 0. If it factors, which it does, x minus 3, x minus 7 equals 0. So x minus 3 equals 0, or x minus 7 equals 0. X is 3, which would make y 7, or x is 7, making y 3. This is the modern approach. Like in a 9th grade algebra class, if they gave you this question, you would have to do it this way or you'd be in big trouble. But the Babylonians had a different approach to this question. And we find in these tablets the description of their algorithm. And I'm going to take you through what their algorithm is. Step 1, they say take half the sum. Step 2 is and square it. Step 3 is to subtract from this square the product. Step 4 is to take the square root of that difference. And step 5 is to add this original number, the half the sum, and the square root that you just got. And that gives us one of the answers. And subtract those two numbers. And that gives you the other answer. So that's an algorithm that's described as clear as anything. I mean, they don't explain why it works. They just say, here are the steps. Take half the sum, square it, subtract the product from that, take the square root of that answer, and add and subtract that from that original number. Hold on one second. Okay, sorry about that. Well, hopefully while I was gone, you looked at this and like thought about it, like, huh, this is interesting. These, why does that work? Well, let's take a look at why that works. Let's say I'll call this S for sum and P for product. So X plus Y over 2, that's our first step. Then we square that. Then we subtract the product from that. And here comes the insight. So the next step is to take the square root of this thing, and it starts to look a little complicated. And it even starts to look like the quadratic formula. And it is similar, I see a comment, it is similar to the process for the quadratic formula, but not because they actually have the quadratic formula. Here comes the major insight now. This expression, before I just throw a square root around it, because that is the next step, this square root of S squared over 4 minus P, it starts to look like the quadratic formula. But the left side, yes, I could write it like this. But that does not give the insight. Here's the insight. Remember yesterday, X plus Y squared minus 4XY is equal to X minus Y squared? If we take that thing, let's go back for a second. If we take that thing and we divide both sides by 4, and then I'm going to just put this 4 into the parentheses, so it becomes X plus Y over 2 squared minus XY equals X minus Y over 2 squared. So that identity follows from this original one. And this thing here on the left is exactly what we ended up with over here. In other words, this actually is the same thing as the square root of X minus Y over 2 squared. So that's why this is so slick, because the square root of X minus Y over 2 squared is just X minus Y over 2. So you see what they do is they cleverly start with X plus Y over 2 and manage to work their way to X minus Y over 2. Let me come to the numerical example. I'm jumping around a lot. Okay. So this 5 is X plus Y over 2. Literally, it's just the X plus Y over 2. But here, this, after you take the square root, this 2 is going to be X minus Y over 2. And when you add X plus Y over 2 plus X minus Y over 2, you just get 2X over 2, which is X. And when you subtract X plus Y over 2 minus X minus Y over 2, you get 2Y over 2, which is Y. So it's really clever how they weave their way from X plus Y over 2 through this clever squaring and subtracting and square rooting, they find themselves at x minus y over 2. And when you add them together, you get x, which is the answer. Or if you subtract them, you get y. So some people I've seen in like history of math books analyze it, and they don't do this step, which is really a missed opportunity. Without this step here, you're totally missing the insight of what's going on. If you just kind of keep going with this thing and say, hey, look, they basically invented the quadratic formula, or they had the quadratic formula, because this thing on the left does end up becoming like the quadratic formula. But it's more clever than that, the way they managed to get from where they are, x plus y over 2, to x minus y over 2 through a clever squaring and subtracting and an application of, I mentioned yesterday, this identity was like the main accomplishment of Babylonian math. And they found all kinds of ways to use it. Let's see. Now, whoops. So that's if you're given the sum and the product. If you're given the difference of the product, the process is almost the same. We take 8 over 4, we square it, not 8 over 4, sorry, 8 over 2, we square it. But this time, instead of subtracting the product, we add product. And that's because this is x minus y over 2. And this thing here is x minus y over 2 squared plus xy, which according to the identity is the same thing as x plus y over 2 squared. So that when you take the square root, you get x plus y over 2. So the only difference here between the two algorithms is that this is a plus here, because I had to take this identity and kind of rearrange it, because I'm going from the given x minus y over 2 and getting to the x plus y over 2. Once I have those two things, if I add them together, I'll get x. That's 11. And if I subtract them, well, once I have if I subtract them, I realize I probably should say 7 plus 4 and 7 minus 4. If I actually subtract this minus this, I get negative 2y over 2, which would be negative y. So just subtract the bigger minus the smaller. So what we've seen today are these two systems of equations so far, the kind where there's a plus there. And so either the sum and the product is given, or the difference in the product is given. And they have this clever 5-step process. Now, not every question is of that form. The sum of two numbers is this and its product is this. We could get back to that original question that doesn't have a y in it. X squared minus 8x equals 33. So that's not the sum and product that are given, or the difference in the product are given. But this is a question they would solve also. Sometimes it would be given, the question would say, find two numbers such that, the sum is this and the product is this. But this is different. This is one saying the square of a number minus 8 times that same number is 33. And their process is to do kind of like the unthinkable, factor out the x. But that 33 is not a 0, so we can't like split this up now. But here's what they notice. If I do a little like substitution, I'll like modern say, what if I say, well, let me replace x minus 8 with y? Then it will say xy equals 33, which is like what we had in the last question where we had a product. But we also have x minus y equals 8, because this is 8 more than that. And now we have the situation from before, the last one I did. 8 divided by 2 is 4. 4 squared is 16. 16 plus 33 is 49. Square root of 49 is 7. 7 plus 4 is 11. 7 minus 4 is 3. So this is a really good example of how they utilize a thing they know, like product and or difference. Sorry, I know how to do the difference in the product, and how to take this other question and, as we say in math, reduce it to the kind of question we already know how to do by doing this unthinkable factor out the x. Now, if this minus was instead a plus, imagine the question said x squared plus 10x equals 56. So they might say this, the area plus 10 times the side square side is 56. You would still factor out the x, still call that y. But what's this other equation? What do you think this other equation is that relates x and y? You can type it in. What do you think this other, what's the relationship between x and y, based on that? So this is a good idea. Like, well, there's a plus here, so it probably changed to a plus. But actually, it's still going to be a minus, but it's going to be y minus x equals 10. You can see from this equation here that in this case, y is 10 more than x. Before, x was 10 more than y. So I kind of threw a little trick question in there because most people do say, well, because this is a plus, maybe there should be a plus there. But regardless of whether this is a plus or a minus, this sign here is going to be a minus, but it might be y minus x instead of x minus y. So now the process is still the same. Half the 10, square that, add it to the 56, take the square root, and then do 9 plus 5 and 9 minus 5. 9 plus 5 and 9 minus 5. Now they're asking what's x, and I have these two numbers, the 14 and the 4. Well, x is the smaller one because there's x and the other one is x plus 10. So for this one, the answer is 4. The 14 is actually not an answer to anything. It's kind of like the value of this temporary value for y. Let me just go back to here for a second. Here I had the 11 and the 3, but for this one, the x is bigger than the y. So x is 11. And you actually don't even need to calculate out the 3. So all you need to do when there's a minus here is the 7 plus 4, like the opposite of whatever this sign is. And all you need to do for the kind where there's a plus there is to do the one where you subtract this number minus that number. Now, the Babylonian tablets just say in words, basically, they have this question: side square, area plus 10 times the side square is 56. And then they just go right into half of 10 is 5. Square of 5 is 25. 25 plus 56 is 81. Square root of 81 is 9. 9 minus 5 is 4. They just say one step at a time, what they do. And it was up to mathematicians, historians to work out the analysis. Okay, the next thing I want to show you is I'm going to take that same question I just did, but show you an alternate way that they used sometimes. Let me go with the x squared one with the x squared plus 10x equals 56. There is a second algorithm that we see evidence of because they describe what their steps are. And this other one is very much related to completing the square. But there's one problem. The Babylonians didn't understand fully how to complete the square. We know now that you complete the square by taking half of b and squaring it. But back then, the only fact that they knew was how to complete the square if there's a 2 there. So for instance, they could solve this question really well. So Ben asked about even numbers. No, I do a lot of even number questions, but no, they would have, they had a pretty good fractional system for halves. So most of their questions actually are fractional. The ones I make up have integers just to practice, but they would use a lot of fractions. How do you complete the square for this bottom question? X squared plus 2x equals 8. This bottom question is like its own question. It's not related to the top one. And that's right, you add 1 to both sides. And the Babylonians were very aware that x squared plus 2x plus 1 was the same thing as x plus 1 squared. That's the one, that's like another fact they had. They knew x squared plus 2x plus 1 is the same thing as x plus 1 squared. Maybe they got that through trial and error. They compared 3 squared versus 4 squared, 9 versus 16, and said, well, how is 16 different from 9? Well, it's bigger by 7, and what's 7? Well, it's 2 times 3 plus 1. Who knows how they came up with that observation, but they knew it. And in this question on the bottom here, we can then say x plus 1. They didn't have negative numbers back then, so I'm just going to say x plus 1 equals 3. X equals 2. Well, that's great if there happens to be a 2x there. But what if instead there's a 10x there? Well, that expression, if all you have is what is it? If all you have is a hammer Everything looks like a nail to you. So they somehow find a way to utilize the only fact they know is that, God, I wish this 10 were a 2. So what they do is they take 10 over 2 and square it to become 25. And they divide everything by 25. Now you look at that and say, well, this is even more complicated than the original question. But look what happens next. I can change x squared over 25 to x over 5 squared. And I could change 10x over 25 right? 10 over 25 reduces to 2/5 to 2 times x over 5. I'll leave that alone. And if you do that process, this is always going to happen, that it's going to become 2, and that these two things are always going to be the same. And you can investigate, why, how can we be sure that that always works? I think if you just say like x squared plus bx equals c, and you, let's call it 2b, might be easier. And then I take half of that, and then if I divide both sides by half of that squared, you can see that this b cancels out with that one, and we get the 2 over b. Sorry, 2 times b over x, and this thing becomes x over b. Anyway, you can mess around with that and convince yourself that this process will always work, and it will always lead us to a thing that looks like something squared plus 2 times something. And now I can add 1 to both sides. And look what I have. I can replace that with x over 5 plus 1 squared. And 56 over 25 plus 1 is 81 over 25. Take the square root of both sides. Don't worry about negatives. X over 5 plus 1 equals 9 over 5. Subtract 1 from both sides. X over 5 equals 4/5. And solve for x. So what I've just shown you is their alternate way of solving this equation. We get the same answer, but it has like a different insight. In this one, the insight is that something squared plus 2 times something plus 1 is equal. This one's based on this insight that u squared plus 2u plus 1 factors into u plus 1 squared. And they find a way to use the little bit that they know. They find a way to like utilize, and it's very resourceful. I mean, they really don't know that much math, yet they're able to do this. So the things they know are u squared plus 2u plus 1 equals u plus 1 squared. And the other thing they know is that x plus y squared minus x minus y squared is equal to 4xy. Just those two facts have come a long way. By the way, I'm not quite sure if they knew even, I'm not sure if they also know that u squared minus 2u plus 1 is u minus 1 squared. Like, I'm not sure if they ever do questions like this with the completing the square process that I just showed you, if that's a minus instead of a plus. They might. The ones I've seen, to my recollection, had a plus here. Okay, the next thing I want to show you is how the Babylonians dealt with a coefficient in front of the x squared. Oh, somebody asked about the y minus x equals 10. That's from over here. That's from over here. Oh, no, it's from over here. So see this x plus 10? That's 10 bigger than x. So they don't add up to 10. Their difference is 10. This is the bigger one. This is the smaller one. So if this thing, x plus 10, is 10 more than x by itself, then it's basically saying x plus 10 minus x equals 10. And I'm calling that y just to do that. Oh, hold on one second. Here, I'm going to put this up on for a sec. Why don't you think about how you might approach this question? Everybody, so I saw this one idea of dividing by 5. And that seems like, well, they're really good at taking the thing they know how to do. And they're not, the Babylonians don't fear fractions so much, although dividing by 5 may not be so bad. But if there was like a 7 in front of the x squared, that could lead to a problem. So they did it a different way. And this is exceedingly clever. Here is what they did. And they didn't divide by 5, believe it or not. But they did kind of the unthinkable. They multiplied by 5. Wow. How could that be good to do? All that does is make all the numbers larger. So you might say, God, how is that a way of getting rid of this 5? By making it bigger? But yes, I see then made a comment that, see, if you multiply this by 5, this number is guaranteed to be a perfect square. So I'm going to write this as 5x in parentheses squared. And this 30x, I'm going to write as 6 times 5x. Because I really want this to match up with this. Notice, if you will, that this 6, oops, that's not what that happened. Notice, if you will, that, sorry, highlight. Whoops. That this 6 will always be the same as that 6 over there. And this is 315. Well, if I do a little, I'm going to do a substitution if you don't mind. They wouldn't do this, but I'm going to just call it u for a second. So u is 5x, and now I have u squared plus 6u equals 315. And I've managed to get rid of, in a sense, the coefficient there, the 5. And now this u squared plus 6u equals 315. That can be solved by taking, if you want, u plus 6. So we take, this is two things whose, if you want to put another variable in and call u plus 6v, we're looking at uv equals 315 and v minus u equals 6. V minus u because the u plus 6 is bigger than u, so it's the bigger one minus the smaller one. And then we can go through the process. Half of 6, square it, add it to the 315, take the square root of that, and subtract. We want to know what u is. U is the smaller one because u plus 6 is the bigger one. So 18 minus 3 is 15. Well, that's the value of u. But remember, u is 5x. So divide that by 5. And you get 3. Which is the answer to that question. So I find this to be like a really clever way of solving this question that's not done, anymore. But it's a nice use of, multiplying is easier than dividing, especially if it's a number like 7 where you don't have a reciprocal, so you can't divide. So that's why they would multiply instead of divide by 5. In this case, they could have divided by 5 because they have, 1/5 is terminating decimal in their number system. Okay, I'm going to finish out today with 3 more questions that are a little bit different than the ones that we saw. One of them is where you're given the sum of the squares and the product. And this question was actually presented as a word problem, and the word problem was this. This type of question is often called the side diagonal question, or the area diagonal question. They tell us that there's a rectangle and that the diagonal is 17 and that the area is 120. Well, the diagonal is the hypotenuse of this right triangle. So this suggests that they know Pythagorean theorem, even though this is 2,000 years before Pythagoras. So they know that x squared plus y squared, that the squares of the legs is equal to the the sum of the squares of the legs is equal to the square of the hypotenuse. So the question was given this way. The area is 120 and the diagonal is 17. We can turn that into that. And there's so many clever tricks. Like in this one, there are various ways of doing this one. Oh, and I see here someone says a high school teacher. So when I teach this, it's in an elective class where they're learning about the Babylonian math. So you see, I like the Babylonian approach if the question says like the sum of two numbers is this and the product is this. But when you have a quadratic equation like x squared minus 5x, it's too many steps to kind of get it into the idea of the sum of two things and the product of two things. I personally like completing the square and then quadratic formula. Now, check out this. You get to use like creativity here. Like, how am I going to deal with these? Well, check it out. If I multiply times 2, I get 240. And then if I take the x squared plus y squared that I have and add on the 240, add on 2xy, that turns into x plus y squared, which is different from x squared plus y squared. And if I take x squared plus y squared and instead subtract 2xy, I get x minus y squared. So what you do is you do 289 plus 240 and 289 minus 240. And you take the square root of those. So 289 minus 240 is 49, the square root of that is 7. And 289 plus 240 is 529, and the square root of 529 is 23. And then when you add those together, you get 2x equals 30, or x equals 15, which makes y equal to 8. So you see, it's like a clever use of, you have to know, that x plus y squared is equal to x squared plus 2xy plus y squared. Then you find a way to like assemble the pieces. Oh, I got the x squared plus y squared. If I only had a 2xy, I could work with that. Oh, well, I can get the 2xy from the xy. So I'm going to throw up here that they also were very aware that x plus y squared equals x squared plus 2xy plus y squared. We kind of imply that they know that because they know the difference, but I'm just going to write those down. I had already their primary fact that x plus y squared minus x minus y squared equals 4xy. You could know this without necessarily knowing these two pieces separately. Like maybe they achieve this third thing, through some other means, like that picture I showed you yesterday with the square, the bathroom tile thing. But they did know these two things also. So that's the area diagonal question. I think I only have 2 other questions. Here's one where the sum of the squares is given and the difference between the two numbers is given. And the trick to this one, it's really clever. Like, we're not going to do substitution or anything. We're going to square both sides of this equation, which means x squared minus 2xy plus y squared is equal to 100. But you see the x squared plus y squared are up here also. So if we subtract, let me subtract the other way. if I do this top equation minus this bottom equation, we end up with 2xy equals 1200, because the x squared plus y squared would cancel out. And xy would be 600. And now we can take the fact that we have the product is 600, and the difference is 10. And I can do the 5-step process. Half the difference, square it, add it to the product, take the square root of that, which actually ends up being 25, and 25 minus 5 is 20, and 25 plus 5 is 30. And the so those are the answers, 30 and 20. 30 is x, and 20 is y, because it's the bigger one. So you can see they get really clever with, there's not that many combinations of things you could be told. Sums of squares is one of them. I think sometimes they have some really complicated ones that have like 3 different numbers. I haven't gone out. I'm going to show you a document that has like some different questions that you're going to mess around with and see if you could find something interesting in them. I'm just going to finish up with the last question of the day. In this one, we're given a kind of funny thing. We're given the product plus the difference, sorry, is 183. And the sum is 27. This is, you know, we talk about questions that are not like so useful, like practical. It's like, why would I ever know these 2 pieces of given information, the sum and then the sum of the product and the difference? Their method is to add these 2 equations together, and they get xy plus 2x, these y's ends up canceling out, is equal to 210. Then they factor out the x. And you see we have now like a product. X times another thing is 210. Well, if I take this equation and I add 2 to both sides, I end up with my other equation. I added 2 to both sides so that I would have the form, the sum of 2 things, in this case x plus, and the other thing is y plus 2, and the product of those same 2 things is 210. So now I can do the 5-step process. Well, we have our first odd number. Oops. We have our first odd number. Half of 29 is 14.5. 14.5 squared is 210.25. Subtract those, subtract this minus this, get 0.25. Square root of that is 0.5. And now I could either get 15, and 14.5 plus 5 is 15. And the other thing is 14. So this could be x, and this thing could be y plus 2, which means the answers would be 15 and 12. Or, because these are added together, the order doesn't matter. So it could be that 14 equals x, and 15 equals y plus 2. There's actually two answers to this question. If you plug in 15 and 12, that will work. Or if I plug in 14 and 13, both of those things will work. Now, those are all the questions I wanted to show you today. Babylonian quadratics and all the different types. I have a homework assignment, written homework assignment. I also have a delta math with some of the cases, not these last three, they're not on the delta math, but all the other ones with the sum and product and things like that. But I'm also going to put up a little project. If I come, let me change the screen share. Okay, I added to the to today's assignment this other thing that says BM 13901. There it is. And what this is 24 questions from an actual tablet. And I'm going to put some more instructions. Like, I think the first question was sideways, but it says I sum the area and my side square so that it was 0.45. That's 3/4. I sum the, so that's saying x squared plus x equals 3/4. And then they go through their process and show how they get half as their answer. And these things get like more and more complicated. By the end, by the 20, I think there's 24 questions, I think. Oh, well, there's 24 questions, except some of them were missing from the tablet. So there are 24, but it says here 21 and 22 were missing. So, so there's 22 questions on this page. And I think as a little project, I'm going to have you, some of these questions are actually on the homework assignment. I put them into modern, terminology, but I'm going to like tell you, pick a question, between 13 and 24 and try to like analyze it yourself. I haven't put that up yet. That's more like a little project. So that's not due tomorrow, but I wanted to show you that. Okay, before I finish up today, if I do a live lesson, it'll probably be an hour. I have made a couple of, I really want people to be able to communicate with each other easily, because when this is a live class and we're like in all together, people usually traditionally like stay after class for an hour and work together and get the homework done, talk about it. But you're all by yourself, you're not able to so much. So I made a Google group, which I tried to invite you to 2 different ways. See if you could get onto that. I made a thing called Piazza, which is like a platform for communicating. Log on to all these different things. I also made a Google Hangout. No one's logged on to any of these things, so I'm concerned that maybe it's being like picky about what emails it allows in. But try to get onto all 4 of those things so I can figure out which one is going to be the one we're going to use. And I guess as a last resort, we could just do old-fashioned emails. Okay, so the Google Hangout, that was problematic for some people, but Ben, were you able to, there's the Piazza is supposed to be a really good one for this sort of thing. It's just a question of whether, did you get the, I put a link to the Piazza on the, in the class page. I put 2 links up today. If you go to the stream, if you go to the stream, you see Google Group, like somehow that you could like add yourself to it, maybe. And then I have here Piazza. Maybe you can add yourself to that. Okay, any questions before? There's a Delta Math due tomorrow and written work, but this project that I've alluded to, I haven't posted the details about that yet. Okay, does anyone have any questions? I see the Google group says you don't have permission. How about the Piazza? Yeah, try the Piazza. That's supposed to be a really good thing. It's funny that I guess City College doesn't have what's called a pro, like a enterprise Google account. They have to pay Google a lot of money. City College pays for Blackboard, but I don't know how to use Blackboard that well. It seems like a big learning curve to do that. If it turns out that's the only way I don't think Blackboard's so great either, because maybe you have to be logged in with your City College email address. So I'm really hoping Piazza works. Christina says Piazza works. So that might be where we ends up. And Blackboard is good. So you've had good experiences with it. Is Christina's Blackboard good for like group chats and things like that?
So Professor, Blackboard has something called a thread, right? You create a thread over there and then we can all comment and we can all post there. So I feel like it's easier, you know, because we all have Blackboard. Blackboard is like, everybody has to have it.
I got you. Okay, so let me investigate Blackboard, and I will get Blackboard on there also, and it'll be like a survival of the fittest. Blackboard will probably, first of all, I have to get it working, which I think I'll get it working by tomorrow, and that might become our go-to place since we're familiar with it, at least you guys are. Okay, I'm going to try to get Blackboard working also, but see what Piazza is also, just to see if that's at least working for today. Okay, everybody. I'm not going to be doing live lessons for a while, so there's going to be videos and Piazza and maybe Blackboard. I wish I could do more of these live ones, but I'm not able to. I have kids at home. I'm actually going away next week, so the next live lesson might be in like a week from Monday. But I'm going to be trying to be on these chat rooms and things like that asynchronously and answering questions that way. And I really hope that the classes help each other and talk about, things. Okay, well, that was a lot today. All the Babylonian quadratics in one day. Okay, everybody. I will not see you tomorrow. It will be a little while.